All right, so this is going to be all about the gas laws lab, where we covered the 3 gas laws: Charles, Boyle's, and Gay-Lussac's. The very first one in station 1 was Boyle's law, so go ahead and turn to that section now. Now it instructed that you need to put together a bottle with a medicine dropper. I used a pipette and put dye into it. So we sucked dye up into the pipette and then we put it into this bottle full of water. So this is what we end up having. And it's easier to see kind of when it's upside down, so we don't have to fight with the lid. So this is what we have. You can see our colored pipette in here with a bubble at the top of the pipette. So remember that these are gas laws, and so we are focusing on the gas bubble. All right, I know it's kind of hard to see, but we're gonna do our best. All right, so this bubble here at the top of the pipette is what we're looking at. And also the stem is also gonna be really helpful to kind of see what's going on. So where is the medicine dropper and why? Well, it's at the top of the bottle. Why is it there? Why is it floating? All right. For part number 2, it says squeeze the plastic bottle. All right, so now this is when we're gonna wanna really pay attention. So I'm gonna squeeze it, and immediately you can see it's really easy to tell that this liquid here in the stem goes all the way back up into the big squeezy part of the dropper, right? You can tell that really easily. Remember that we really want to focus on this bubble up here. So when we squeeze it, we're going to look at this bubble and you can see that the bubble gets tinier. It squishes up. All right, so when we increase the pressure, the volume reduces. All right. And that is our demonstration of Boyle's law. When you increase the pressure, the volume decreases. Those two are inversely proportional to each other. All right, our next one is station number 2, which is Charles' law. Charles' law talks about temperature and volume. All right, so we have 2 things here. We have something cold. I have a bucket with ice water. And then we also have something hot. All right, so we also have something hot, which is a hot plate with some boiling water on it. Now we have a balloon here and I've blown it up so it's about the size of like a small melon or maybe like a large grapefruit or pomelo. And I've drawn these circles all over it. Now the reason I've drawn the circles is because it's kind of easier to see if it's growing or shrinking when you have something on it to kind of gauge, right? Because it doesn't have like this crazy drastic change. All right, so the instructions say, the instructions said to use a hairdryer, but I forgot the hairdryer. So here we have our hot plate, and we're gonna use steaming water to do it. So we're gonna put our balloon here on the steaming water. Let's pick a good side. So this side has a lot of circles on it, so that's the part that I'm gonna put here down onto the heat. And we're gonna put it there. Now, if you watch it really carefully, you might be able to see that it's definitely expanding here on top of this roiling boil. Yes, it is growing quite a bit, actually. Awesome. It's a very hot steam and a hot plate. All right, so let's take it off, see if we have any marked difference. You can see that our circles are definitely bigger than the circles on the other side. So there was absolutely some expansion there. Put it on a little bit longer, see if we can get optimal expansion. Do it on this side where it's really loose still. Yes, you can see the balloon like readjusting because it's getting bigger and it's harder for it to sit into that beaker there. All right, so I'm gonna scoot this over here a little bit out of view and bring in our ice bucket. All right, and we're gonna dunk our balloon into this ice bucket. You can see it's nice and big. The circles have definitely gotten bigger. Now we're gonna dunk it in here, and I know it's hard for you to see this. I will show it to you after it's been chilled. We're just gonna rotate it around a little bit. So now we're trying to cool that gas down in the balloon. We're trying to cool it, cool it, cool it. Ooh, that is cold water. All right. Let's see how our balloon is now All right, look how much smaller that got. You can tell the circles got smaller for sure, especially down here at this part. You can see how much smaller those circles got than when they were big, after it had been heated, right? It got much bigger. Now they're much smaller than they were. All right, which proves that when we heated it up, it got larger, and then when we cooled it, it got smaller. Now, I think that the change from room temperature to hot was fairly slight, right? It wasn't that super noticeable, wasn't huge, but the difference from hot to cold was quite noticeable. I think that the change from where it was after it was heated to where it is now was definitely more noticeable. You can see in the light how much thicker, how much more condensed it got right here in this section because we put it into the cold water. Just gonna put that in there. All right, our last one to do is going to be Gay-Lussac's Law, and for that one, we need to go to the next station. All right, we're gonna go over to the hood where we do the fire. All right, so here we have our setup. So what's really important to note here is we have a Bunsen burner. It's not hot, obviously, I can touch it. We have a ring stand with a piece of mesh on it. And then we have an empty can here. We're gonna put a little bit of water here into this empty can. It's just about 10 milliliters, not a ton of water. Just a little bit is all we need because we are gonna wanna turn that water into vapor is what we're looking to do. So I'm gonna turn on this Bunsen burner. All right, so we have the Bunsen burner turned on, and that's gonna heat up the water inside of the can. Ooh, let me see if I can turn this so that you guys can maybe see the steam. Bam, I have the black paper there to help us see the steam a little bit better. It just shows up better on a black background, right? So we're gonna wait for that to be really boiling with steam. And then when it's ready, we're going to flip it upside down using grabbers and put it into this cold water that I have right here. There's a little bit of steam coming out. You guys hopefully can see it in the video. It's starting to come out. It's a little bit more intense. We want most of the water to be gone before we flip it over. All right, here we go. All right. So let's get you guys a better view of that. I'm gonna kind of cool the can off here a little bit so that I can touch it. All right. I'm gonna turn off the gas. All right, let's see what happened. Wow, so we put it into the water and it crushed, and it didn't just like slowly crush, it immediately crushed the can. Right? This is a pretty intense crushing. So it's from all angles and it just kind of implodes is what it looks like there, doesn't it? I have some examples of other cans. This is a bigger soda can and you can see it like just sucked it right in, right? All right. So let's talk a little bit about why. Why did that happen? Well, let's think about what law we're looking at. We're looking at Gay-Lussac's, which is all about pressure and temperature. When you heat up that gas on the inside, right? So you're heating it up. We know that the gas inside the can is 100 degrees Celsius. It has to be because it's boiling water, right? That's the temperature that water boils at. So our gas is at 100 degrees Celsius, but because the can is open, it's still at 1 atm, right? It's still at atmospheric pressure. And so we have 100 degrees Celsius at atmospheric temperature. And then when we put it into the cold water, the gas inside the can cools down very rapidly to maybe 30 degrees Celsius. So that's like a 1/3 reduction or a 2/3 reduction of where it had been. And so the pressure is also going to reduce by about 2/3 because they are directly proportional. So now the pressure inside the can immediately becomes very low. It was at 1 atm and now it's at like 0.3 atm. And the pressure outside the can is still 1 atm, right? It's still 1 atm outside because it's still atmospheric pressure. And so the reason that the can implodes like that is because of the difference of the pressures, right? It's 1 atm on the outside and about 0.3 on the inside. And so that pressure on the outside is going to push that can in and crush it, just like how we saw happened. All right, so I hope that this was a helpful review of the lab, and use it to answer your lab questions, review it, go through it, pause it, do whatever you need to do to use it to help you get this lab done. All right, I hope this was a helpful tool for you. We'll see you guys next time.